So until 1829, pretty much the greatest scientific minds on Earth believed organic chemistry was, well, literal magic.
Oh, yeah. Completely magical.
Right. They were totally convinced it was powered by this invisible, um, vital force that only living things possessed.
Which is just so funny to think about now.
It is. But today, we are going to help you use the shattering of that exact historical myth to, cure your students' end-of-term exhaustion. So welcome to the deep dive.
We are so glad you're here.
Yeah, we are basically acting as your expert study partners today, helping you, our absolute favorite Oregon Community College chemistry professor, prep for the final super crucial unit of your Adams First General Chemistry sequence.
Exactly. We're diving deep into Chapter 23 of Julia Burge's textbook, Chemistry, Adams First.
The big one.
The big one, yeah. Organic chemistry. And since you are, navigating this final stretch of the spring term, we know your goal isn't just to barrage them with facts.
No, they're already exhausted.
Right. So the mission here is to anticipate exactly where your students are going to stumble, dismantle those classic misconceptions, and arm you with strategies that make these foundational concepts just, well, click.
Before they even look at a complex synthesis problem.
Exactly.
Okay, let's unpack this. Because, as you know, organic chemistry is like the ultimate boogeyman for undergrads.
Oh, absolutely. They walk into the lecture hall expecting just an impossible mountain of shapes to memorize.
Yeah, it's super intimidating, which is why opening your first lecture with that myth of vitalism is such a brilliant pedagogical hook. You aren't just handing them a syllabus, you're, showing them a literal scientific revolution.
It completely reframes the subject, because for centuries the assumption was that you could never synthesize an organic compound in a lab. It was fundamentally impossible.
Because a beaker doesn't have a soul.
Right. A beaker has no vital force. But then Friedrich Wöhler comes along in 1829, takes two perfectly mundane inorganic substances.
Lead cyanate and aqueous ammonia, right?
Yep. Lead cyanate and aqueous ammonia. He heats them up and bam, he produces urea.
Which is undeniably a biologically organic compound.
Completely organic, made entirely from scratch in a lab.
No magic required.
No magic at all. Wöhler's synthesis proved that organic compounds follow the exact same physical rules as the inorganic compounds your students have been studying since the fall term.
And that right there is the crucial pivot for an Adams First curriculum. You can leverage that historical aha moment to connect directly back to the atomic structure they spent the whole fall term mastering.
It's the perfect bridge.
It really is. You've spent months hammering home like quantum numbers and electron configurations. Now you get to show them the biological payoff of all that work by answering one fundamental question.
Why is carbon the undisputed king of the elements?
Right. And you've probably seen students make this exact intuitive leap, and it's a great misconception to anticipate. They look at the periodic table, they see carbon sitting in group 4A, period 2, and they know its electron configuration makes ion formation, well, energetically impossible under normal conditions. So it forms 4 covalent bonds.
But then they look right below carbon.
Exactly. They look right below it and see silicon. And they ask the inevitable question. Well, silicon has 4 valence electrons too. Why aren't we carbon-based and silicon-based?
Why isn't there a whole branch of biology dedicated to silicon? I love that question.
That's a great question.
It really is, because it exposes whether they truly grasped atomic orbitals. And this is where you can deploy a really vivid analogy to explain the why behind the chemistry, not just the what.
Right. I mean, I've heard some instructors use a basic comparison, like saying carbon is like Lego and silicon is like Velcro. It just sticks to everything.
Yeah, the Lego and Velcro thing. It's okay.
It's okay, but it doesn't really explain the physical mechanism to a community college student.
No, it doesn't.
So what if we evolve that analogy? What if we compare carbon to a perfectly packed, hard-shell carry-on suitcase? Like, everything is zipped up tight in that second shell. There are absolutely no extra compartments.
I love that. That is a much more mechanically accurate way to teach it, because the reality of that Velcro behavior comes entirely from the d orbitals.
Right.
Carbon's valence electrons are in the second shell, where n equals 2. There are no d orbitals at all. It is a smooth, hard shell suitcase.
But silicon's valence electrons are in the third shell.
Exactly, n equals 3. And the third shell does have d orbitals.
Even if those d orbitals are empty, they exist physically in space around the atom, right?
Yes, I do.
Yeah.
So silicon is less like a hard shell carry-on and more like a hiking backpack covered in all these empty, unzipped side pockets.
That is precisely the image you want in their heads. Those empty pockets The empty d orbitals are incredibly vulnerable.
They act as perfect target sites for lone pairs of electrons from other substances to just swoop in and attack.
Which is why silicon compounds are staggeringly reactive compared to carbon.
It's so reactive. You can actually put Burge's side-by-side textbook example right on your slide to make this super concrete for them.
Oh, showing ethane next to disilane.
Yeah. Show them ethane, 2 carbons and 6 hydrogens, next to disilane, 2 silicons and 6 hydrogens. The contrast is dramatic.
Because you can leave ethane sitting in a beaker exposed to air and water, and it does absolutely nothing.
It is totally stable. But disilane, because of those unzipped side pockets catching every passing lone pair, it breaks down rapidly in water.
And it combusts spontaneously in the air, doesn't it?
Spontaneously, yes.
That's wild. By showing them this, you prove that carbon's unique lack of d orbitals is the only reason it can perform catenation.
Right, forming those endless stable chains that make DNA and proteins possible.
It completely grounds the magic of biology in the hard physics of atomic structure.
It's a great light bulb moment for them.
Definitely.
Yeah.
So, okay, once you've established why these massive carbon chains exist, the next major hurdle is teaching the students how to actually read the maps of these chains.
Yes, the nomenclature.
The textbook lays out the IUPAC rules. But the real cognitive leap for the students is mastering bond line structures.
The shorthand. It is an incredibly elegant linguistic tool for chemists, but for a student seeing it for the first time,
It's terrifying.
it feels like learning a highly exclusionary secret code. I mean, they are looking at zigzag lines where the carbons aren't drawn, and crucially, the hydrogens attached to those carbons are entirely invisible.
And this brings up a massive pedagogical debate, and I actually want to push back on the standard approach here.
Okay, let's hear it.
If we skip drawing all the hydrogens, aren't we just setting them up to fail? I mean, we've both seen the downstream effects. Students look at a bond line structure, they completely forget the hidden hydrogens exist, and they miscalculate the molecular formula.
Oh, all the time.
It ruins their stoichiometry, it ruins their mass calculations. If this shorthand causes so many critical errors, why not just force the training wheels?
What do you mean?
Like, why don't we mandate that they draw every single Kekule structure with all the carbons and all the hydrogens explicitly drawn out? Wouldn't that prevent the mistakes entirely?
I mean, I completely understand the temptation. Dealing with those stoichiometry errors on exams is incredibly frustrating.
It really is.
But if we connect this to the overarching goal of organic chemistry, forcing them to draw every single hydrogen actually cripples their chemical intuition.
Wait, really? How does being more visually accurate cripple their intuition?
Because organic chemistry is fundamentally about pattern recognition and reactivity.
Okay.
And reactivity happens at the functional groups, not along the boring hydrocarbon backbone. Think about the visual cognitive load on the student.
Right, if there's too much to look at.
Exactly. If you make them draw a 20-carbon chain, and they explicitly draw all 40-something hydrogens around it, the molecule just becomes absolute visual noise.
It's like handing them a map where every single tree, rock, and bush is drawn in excruciating detail.
Yes. They will never be able to find the highway. They get completely lost in the irrelevant details.
So the invisible hydrogens aren't just a shortcut for lazy chemists.
Not at all. They are a deliberate visual filter. You kind of have to endure the growing pains of those early stoichiometry errors because you are training their eyes to ignore the unreactive backbone.
Ah, I see. Because heteroatoms like oxygen, nitrogen, the halogens, those are always drawn explicitly in bond line structures.
Exactly. If a student can look at a stark zigzag line and instantly lock onto the explicit oxygen of a carbonyl group, they immediately understand the molecule's properties.
They know exactly where the chemical reaction is going to happen.
Right. But if that oxygen is buried in a sea of explicitly drawn H's, they miss the forest for the trees.
So the shorthand is actually a pedagogical tool to force focus. That makes a lot of sense. You have to push them through the discomfort so they can actually see the chemistry the way a professional does. Okay, so once they can read that 2D map, the next major hurdle is pulling those flat drawings off the page and forcing the students to visualize them in 3D space.
Which is incredibly difficult for a lot of learners.
It really is. I mean, the textbook introduces constitutional isomers molecules with the same formula, but connected differently, which is, easy enough to grasp on a flat page.
Yeah, that's just moving the pieces around.
But then you must introduce stereoisomers, and specifically chirality, which is entirely reliant on 3D spatial awareness.
And that's where brains start to hurt.
Oh, big time. When you introduce a chiral carbon, a carbon with 4 completely different groups attached to it, you are introducing the concept of enantiomers.
The left-handed and right-handed versions of the exact same molecule.
Right. They are mirror images, but they don't superimpose, just like a person's left and right hands.
But instead of just using abstract wedges and dashes on the whiteboard to explain this, you have an incredible opportunity to use real-world stakes.
Yes. The textbook's pharmaceutical examples are perfect for this, because abstract shapes don't motivate exhausted spring term students, but like billion-dollar corporate loopholes definitely do.
Oh, they love the drama.
They really do. The Prilosec and Nexium story is a phenomenal teaching tool for chirality. You can tell your class about AstraZeneca's patent on the blockbuster heartburn drug Prilosec.
Right, which was originally sold as a racemic mixture.
Exactly. It contained a 50-50 mix of both the left-handed and right-handed enantiomers of the molecule omeprazole.
But biological receptors in the human body are themselves chiral. They act like highly specific locks.
So only one of those enantiomers actually fits.
Yes, only one specific 3D shape fit the lock and acted as the therapeutic drug. The other enantiomer was essentially just useless powder going along for the ride.
Doing absolutely nothing. So when AstraZeneca's patent on Prilosec was about to expire, and they were, staring down, losing billions in revenue to generic brands, they used chirality to save their monopoly.
It was a very clever move.
Extremely clever. They isolated just the active, therapeutically effective enantiomer, esomeprazole. And because it was physically distinct from the racemic mixture, they were able to patent it as a brand new drug.
Nexium.
Nexium, the famous purple pill.
It is the exact same chemical conductivity, just the purely active 3D shape. It so powerfully illustrates to the students that in biological systems, three-dimensional geometry is not just like a structural trivia fact.
No, it dictates the entirety of a molecule's function.
Exactly. Now, the textbook also covers how we physically measure this chirality in a lab using a polarimeter, because chiral molecules rotate plane polarized light.
Right, which is fascinating. Like, we experience polarized light at 3D movies when the glasses filter light differently for each eye.
Yeah, that's a great everyday example.
But considering the pacing of the term, I have to ask, do you really want your students bogged down in the actual schematic of a polarimeter?
Honestly.
I mean, memorizing the fixed polarizer, the analyzer tube, the light source, but it feels like testing them on machinery rather than chemical principles.
That is a very critical point about scope. As a professor trying to prioritize conceptual foundations, I would highly recommend skipping the memorization of the polarimeter machinery entirely.
Yeah, just gloss over it.
Totally. Focus that limited lecture time entirely on the spatial concept of chirality itself. In fact, if you want to dedicate time to a complex structural concept, spend it on resonance.
Oh man, resonance. That is another one of those concepts where students tend to get lost in the rules rather than the reality.
They really do.
They learn that some molecules can't be represented by a single Lewis structure, so we draw multiple structures and say the real molecule is a hybrid. But they often just treat it like, moving puzzle pieces around on a page.
Which is why tying it to ATP, adenosine triphosphate, is such a powerful strategy.
Especially for your students heading into nursing or biology programs.
Yes. You've already taught them that ATP is the molecular energy currency, but resonance explains why it holds so much energy.
Because when ATP hydrolyzes, when it reacts with water to break a phosphate bond and release energy, it forms a hydrogen phosphate ion.
And the reason that reaction is so energetically favorable is because that resulting hydrogen phosphate ion is incredibly stable.
And it's stabilized by resonance, right?
Exactly. The negative charges on the oxygen atoms aren't localized. They aren't stuck on a single atom just repelling each other. They are delocalized, basically smeared out over the entire phosphate group.
Which lowers the overall energy. And when you teach them to draw this, you are going to be using curved arrows to show the resonance structures.
Yes, the arrows.
And this is where you have to lay down a foundational rule, right? Resonance arrows show the possibilities of where the electron density exists in the hybrid reality.
They do not show the literal movement of electrons from one moment to the next.
And that distinction is paramount.
Because it sets up the final, most crucial unit of the term, actual chemical reactions, where the arrows actually do represent physical movement.
Right. You've built their understanding of the atomic structure, you've taught them to read the shorthand maps, you've forced them to see the molecules in 3D.
And now you teach them how these molecules physically crash into each other.
The engine of chemistry.
Exactly.
The textbook categorizes reactions into addition, substitution, elimination, and isomerization. But rather than having them memorize those categories as isolated lists,
Which is what they'll try to do.
oh, they will definitely try. But the pedagogical key is getting them to grasp the underlying choreography. You are teaching them the fundamental dance between nucleophiles and electrophiles.
You can distill almost all of organic chemistry down to this one interaction.
Okay, break it down for us.
A nucleophile is electron-rich. I have a lone pair of electrons, and it is looking for a nucleus, a positive charge, or a partial positive charge to share them with.
It is the attacker.
It's the attacker. And the electrophile, conversely, is electron-poor. It is the target.
So the nucleophile is essentially a molecular predator searching for a positive charge.
I like that, yes.
But this is where we hit what might be the single biggest conceptual roadblock in all of organic chemistry.
Yep, I know exactly where you're going.
Students have spent their entire lives observing macroscopic physics.
Yeah.
They know how magnets work. They know that positive attracts negative.
Right.
So when you put an electron-rich nucleophile and a positively charged electrophile on the board and ask them to draw the mechanism arrow, their instinct is to draw the arrow starting at the positive charge and pointing to the negative charge.
Because, in their minds, the powerful positive charge is pulling the negative charge toward it.
Exactly. How do you break that ingrained intuition?
You have to fundamentally reframe their understanding of what the positive charge actually is.
Okay.
You have to drill into them that mechanism arrows do not track abstract forces like magnetism. They track the physical, literal flow of mass, they track the electrons, and electrons are negative.
So you can't move a positive charge in organic chemistry because the positive charge is just an empty space.
It's a void where electrons used to be.
That makes total sense. You can't draw an arrow originating from an empty space.
Exactly. The electrons are the physical entities doing the moving. So the arrow must always unequivocally start at the source of the electron, the nucleophile's lone pair, and point to the electron-deficient atom, the electrophile.
You are mapping the flow of physical reality.
Yes. And Burge's text gives a brilliant, crystal-clear example you can use to model this on the whiteboard.
The carbocation.
The carbocation. Imagine a carbon atom that in the middle of a reaction has somehow lost an electron pair.
So it is now surrounded by only 6 electrons instead of its highly stable octet.
Right. And it bears a full positive charge. It is desperately unstable. It is the ultimate electrophilic target.
So you draw a nucleophile next to it, like a bromide ion with a full negative charge and plenty of lone pairs.
And you physically show the students how to place their dry erase marker directly on the bromide's lone pair, swoop the arrow over, and point the head of the arrow directly at the positive carbon.
You are visually demonstrating the lone pair flowing through space to form the new covalent bond.
Exactly. And to make sure this isn't just an abstract exercise, you tie it back to the biology examples they actually care about.
Like protein digestion.
Yes. You show them that the digestion of proteins in their own stomachs starts with this exact kind of nucleophilic attack.
Oh, wow. And even the ATP hydrolysis we discussed earlier.
Yeah, that entire process begins with a water molecule acting as a nucleophile, using its oxygen lone pair to attack the electrophilic phosphorus atom in ATP.
It is all one interconnected system.
It really is. And when you teach it this way, you aren't asking them to memorize 100 disjointed reactions. You are teaching them to read the logic of the molecules.
Right. Once they understand that nucleophiles attack electrophiles and that the arrows simply trace the physical flow of electrons.
They can predict the outcome of reactions they have never even seen before.
And that really is the ultimate goal for your students as you prep this final unit. You are building a conceptual foundation that will carry them right into their advanced biology and nursing courses.
Absolutely. So looking back at the roadmap we've laid out for this chapter,
Yeah, let's review.
you start by leveraging their fall term knowledge, using carbon's lack of d orbitals, the hardshell suitcase, to explain why it forms the stable backbone of life.
Then you push them through the visual growing pains of bond line structures so they can instantly recognize reactive functional groups.
Right. And then you pull them into 3D reality using the high-stakes corporate drama of Nexium to prove that spatial geometry is a matter of therapeutic life and death.
And you culminate with electron-driven mechanisms, breaking their macroscopic intuition by teaching them that arrows trace the true physical movement of electrons from the nucleophile to the electrophile.
It is a masterful sequence to teach.
It really is. But before we sign off, I want to leave you with one final provocative thought to take into your classroom, something you can use to, set the stakes for the entire term.
Oh, I love a good cliffhanger.
At the very beginning of chapter 23, Burge touches on the concept of bioprospecting.
The ocean pharmacy.
Exactly. 79% of our planet is covered by oceans, and those oceans are essentially a massive, untapped, and largely unexplored pharmacy.
Scientists are diving deep into reef ecosystems, looking at marine microorganisms, corals, and sea sponges.
And they're discovering profoundly potent organic compounds. They are finding natural lead compounds with extraordinary anti-inflammatory, antiviral, and anti-cancer properties.
But discovering a compound in a sea sponge doesn't cure anyone.
No, it doesn't. Once that lead compound is found, it is handed over to an organic chemist.
And that chemist has to decipher its complex bond line structure
They have to identify every single chiral center.
and systematically map out the exact nucleophilic substitution mechanisms required to synthesize that molecule from scratch in a laboratory.
That is the only way a rare sponge extract becomes a globally accessible drug.
It is the ultimate real-world application of every single concept you are teaching in this final sequence.
So as you stand in front of that exhausted class on a rainy Oregon morning, trying to get them to understand why the mechanism arrow must start at the lone pair. Ponder this.
Yeah.
How might you use the mysteries of the ocean to inspire that one student in the back row? To make them realize that the abstract mechanism they're struggling to draw on their exam today might be the exact blueprint they need to synthesize the next major ocean-derived cure tomorrow.
That is a powerful why. It elevates the material from a textbook requirement to a tool for changing the world.
It truly does. So what does this all mean for your students? It means they are building a conceptual foundation, not just memorizing formulas. Thank you for joining us on this deep dive into Chapter 23. Good luck with the final stretch of your term, and as always, keep unpacking the world around you.
Happy teaching.